For section 3.3, we're going to discuss measures of variation. We've seen most of these first parts before, so I'm going to emphasize kind of what we need to know. We've talked about range before, the max minus the min, easy to find, rough idea of variation, kind of tells me the spread of the data. Another question we should keep discussing as we go is, are these resistant to outliers? So when I'm talking about the range, I am taking the max minus the min. So is that resistant to outliers? Well, short answer is no. Why? Well, if I'm calculating the range, if we have an outlier, it will either be the max or the min. It will be one of those extreme values. So range is not resistant. It is affected by outliers. What about standard deviation? It's tempting because you're looking at this going, well, this uses all these numbers, so it's resistant to outliers, but it is still not resistant. It's more resistant than the range, but the idea is what? We take all the numbers minus the mean. That means we include all the numbers. We use the mean, which is calculated using the actual outlier, and we use the outlier as part of the standard deviation. So an extreme number will change the standard deviation. So the standard deviation is also not resistant. When we're using the term variance, variance is taking that standard deviation and squaring it. So basically we go through the formula before we square root it. That is called the variance. That is also not resistant. So the idea is basically everything we're using in this section is going to be non-resistant. There are measures of variance that are kind of a measure of spread that will be more resistant. That's not what we're going to be focusing on in this section. So keep in mind also that we need to know some basic symbols. So for our symbols, we already have S for standard deviation and S squared for variance, but keep in mind that those are the symbols for the sample statistics. So sample statistics would be things like standard deviation, variance, sample size, mean. All of those are sample statistics. They're from our sample. Versus over here, if we talk about the population parameters, those are the numbers about the population, and that would include, so here we have standard deviation of the sample, here we have sigma, the standard deviation of the population. This would represent sigma squared, would be the variance of the population. Just like we have a lowercase n here, we have an uppercase N for the population size. And just like we have mean, we have mu. So make sure that we are understanding that there's a difference between these two symbols. I think they talk a little bit about this specifically with variance, but I wanted to make sure I discussed it. The range rule of thumb is, let's see, this is not as important to me. What I'm going to emphasize more than the range rule of thumb will be the empirical rule. And it goes a little bit beyond just the range rule of thumb. The empirical rule is also known as the 68, 95, 99.7 rule. You're like, well, that's a really weird name. Okay, well, here's the idea. If I have a normal distribution, in the center, if it's perfectly normal, would be our mean. And going to the right, each of these would represent one standard deviation. Okay? What the empirical rule says, so this would be the mean, let's see, plus one standard deviation. This would be the mean plus two standard deviations. This would be the mean plus 3 standard deviations. Going backwards, mean minus 1 standard deviation, mean minus 2 standard deviations, and mean minus 3 standard deviations. What the empirical rule says is that within this one standard deviation, we have 95% of the data. Oh, geez. I'm a liar here. Sorry. Thinking. First number is 68. So within one standard deviation, we have 68%. 8% of the data. Within 2 standard deviations, we have 95%. That's what they were saying here with this range rule of thumb. But there's more numbers than just the 95 you need to know. So within 1 is 68, within 2 is 95, and within 3 must be the last number, 99.7% of the data. And we're going to play more with that as we keep going. Okay? There is a way of estimating standard deviation. So if I take the range from the max minus the min and I divide it by 4, then I'm going to get an approximate standard deviation. There will also be some questions on the coefficient of variation in your homework. All of this is not tested. It's an interesting discussion. It's good to go over. But what do you really need to know from this? You need to know the symbols. You need to know if something's resistant. And you need to know the empirical rule. And so I'm going to spend a little more time on the empirical rule because that's what I'm going to quiz on the most, and that's what you're going to have mostly on the test. So here's a bigger version of our normal distribution. And see if I can scoot this over. There we go. So we already said that within 1 standard deviation, okay? Oh, so real quick, right here, these were x's. This also works if we convert it into z-scores. So the z-score is how many standard deviations we are from the mean. So when I go down here, this 0 represents the mean. This represents the mean plus 1 standard deviation, the mean plus 2 standard deviations, the mean plus 3 standard deviations. These are our x's on the bottom, and above these are our z-scores. Z-score, basically the number of standard deviations a value is from the mean. So a z-score of 0 means you are 0 from the mean. That number ends up being the mean. If you are 1 standard deviation above, you would have a z-score of 1, 2 above, 3 above. And going backwards to the left of the mean, this would be a number below the mean. So that would be the mean minus 1 standard deviation, mean minus 2 standard deviations, mean minus 3 standard deviations. So here's what we knew already using the empirical rule. We know that within 1 standard deviation we have 68% of the data. I'm going to go ahead and do this as a decimal this time. So 0.68. And let's see if I can change the color there. There we go. 0.68. Okay? So if we have 68% of the data within 1 standard deviation, what must each of these pieces be worth? Well, since we know the normal distribution is symmetric, basically I have 2 pieces that total up to 68 and they're identical. So if I take that 0.68 and I cut it in half, each of these is worth 34%, 0.34. So each of these pieces, if I was to add them up, would be 34%. So if I took the area of these 2 pieces, each one would be 34, and so they would total 68. If I go within 2 standard deviations, we said that was 68.95. So as a decimal, 0.95. Now here's the problem. Yeah, that means these 2 pieces are, I guess, half of that 95, or 47.5. But I really want to know, what are these little pieces worth? Okay, so what are those little pieces worth? Well, we went from 68 to 95, which means we added, what is that, 27%. I can take that by saying we were now at 95%. We came there from 68%. So if I subtract them, I've gone up 27%. That means that these 2 green pieces are worth 27%. They've added 27% to get from 68 to 95. Well, if those pieces are the same size, the same value, then that means I can take this and divide it by and each of those pieces is worth 13.5%. Well, what are these last pieces worth then? Well, we know that within 3 standard deviations, we have 99.7%. So, let's see if I can, nope, dang it. Undo. 99.7. So, that would be 0.997 within 3 standard deviations. So once again, what are these little pieces worth? Well, we went from 95 to 99.7. So how much did we add? How about 4.7%? So what are each of those worth? If they're the same, cut them in half. 0.0235. 0.0235. What's left? What are these little pieces on the outside worth? Let me color code just to make sure we're clear here. So that's these little pieces right here and right here. Okay. What are the little pieces on the outside worth? Well, if everything on the inside here is worth 99.7, then I can do 1 minus 0.997 means I got a measly 0.3%. So that makes each of those 0.0015. Really tiny pieces. So what would happen if I added up all these numbers here along the bottom, right? Well, ideally they should add to 1, right? So we have 0.0015. So let's go and do that. Let's go to here we go. So 0.0015 plus 0.0235, I think. Let me double check. Nope, 0.13. Nope, 235. Hey, look at that. 0.0235 plus 0.135 plus, what was that one? Half of 68, so 0.34. So 0.135. All right, so I'm going to stop at this point. What I've done is I've added the first 4 pieces. So I've added 1, 2, 3, 4. What should these 4 total up to at this point? Well, it's half of the diagram, right? So I'm going to just stop right here and go, well, this should add up to 50% of the overall picture. And then it would make sense that if I did this again, I took this and then I added the rest on the right side, the other 0.34, the other 0.135, the other 0.0235, and last 0.0015. This should total to 100% or all of it, okay? So you're like, well, why are we breaking this into pieces? Because there are times that we're going to basically go, what's the probability of a z being between certain values? And if it matches one of the numbers from the empirical rule, then it's easy. And if it doesn't, then we're going to need to basically use these pieces to add them up. 68, 95, 99.7 rule. Okay. So to that example, we're going to use the empirical rule to find the probability between -2 and 2. And notice I don't have an equal sign here. That's not really relevant in the situation. We're dealing with a continuous variable. So if I said something like, what's the probability of x equaling 2? Okay, you're basically saying, what is the area of this line right here? Because the probability is the area under the curve, and we're talking about the area of a line. That would be like, what? Area is length times width, space inside. This line would have no area, so this would equal 0. So when we're using these, we have to have ranges to find the probability under a curve, because we're dealing with continuous variables. So I'm going from -2 to +2. I've got a couple options. I can go from -2 to +2, and I can add up these 4 numbers. So that would be 0.135 plus 0.34 plus 0.34 plus 0.135. I can take those pieces and I can add them up. But using the empirical rule, we know that within 2 standard deviations should be 95%. So if I add those up, they will add up to 95%. But you don't have to add those up because we know the empirical rule tells us it's 95%. But this says, well, what about between -1 and 2? See, what happens is I'm not including all 4 of these numbers. I'm only including from -1 up to the 2. So that I'm including this 0.34, this 0.34, this 0.135. So that excludes this first number is no longer down here. We would just keep the other 3. And so I can add those up, and that would be 68, 70, how about 0.915? No, that's ridiculous. How about 0.815? Jeez. All right. And so that's how I would do that. If they give me numbers that are on the empirical rule, I would just use the empirical to go straight to that. But if it's not, then I would add up the pieces that we just calculated. So between -2 and 0, I would add up the 2 pieces between that area. So I would add up the 0.135 and the 0.34. So what is that, 475? Now somebody else is going to go, well, that's half of the answer for number 1. You basically have stopped at 0 instead of going on the other side. That doesn't bother me at all. So if you did 0.95 and you cut that in half, I'm fine with that. There's other ways of doing this that are not necessarily wrong. I'm just showing you that what I would recommend is that you add up the pieces. Less than 1. Now what this is doing is this is saying start at 1 and go less than, go to the left. So all of those values. So I could take this 0.34, 0.34, 0.135 and add all of them to the left of that. So that would be what's the first one? 0.0015 plus 0.0235. Double check that. Plus 0.135 plus 0.34 plus 0.34. Okay, so I've added everything to the left of that 1. Now this is not how I would do this, but this would work. You could take all of those pieces, 1, 2, 3, 4, 5 numbers. Let me make sure on that. 1, 2, 3, 4, 5 numbers. But what I would do is I would say what? Everything to the left of 0 should total to 50%. So I don't need all those numbers because I know that all of these total up to 50%. And so all I need to do is add that one little piece there. I would just take everything to the left of 0 and go, well, that's half of the diagram. That's 50%, plus 0.34 is 0.84. Either way, if you add up all the pieces, or you say 0.50 plus 0.34, either way you get 0.84. How would I do greater than -1? Let's go back to the picture. Greater than -1 means I'm going -1 and to the right. I can add up all 5 of those numbers. Or I can say what? All of these add up to 50% plus the other 34. So I go 0.84, 0.50 plus 0.34, 0.84. Some of you are going, well, wait a second, that's cool. This is the same answer. This should be. This has symmetry. So if I'm going from +1 and to the left, that should be symmetric from going to -1 and to the right. I'm adding a half plus 34, and a half plus 34. Those answers should be the same. So if you notice that, good for you. That's actually really good. How would I go from -3 to 2? I could add up all the pieces, starting with 0.015. No, that one's not included here. Starting with 0.0235, 0.135, 0.34, 0.34, 0.135. I can add up all those pieces. Make sure I did that right. So that would be going from -3 all the way up to 2. So I start at the 0.0235 and I end at 0.135. Okay? Or I know that from -3 to +3 is 99.7, and I can take away the piece that's missing. I know that between -3 to +3 is 99.7, and I'm including all of that except for this 0.0235. So I could take away 0.0235. You're like, I don't know, that's insanity. Well, find something that makes sense for you. But what do we do? 0.0235 plus 0.135 plus 0.34 plus 0.34 plus 0.135. Or I said take 99.7 and take away the piece that's missing. Two ways of getting that same answer. And what was it? 0.9735? I need more space. And greater than 2, I can take and add these two pieces, 0.0235 plus 0.0015. And what would that be? 0.025. Or I could take everything to the left of 2 and that would leave me everything to the right of 2. So I don't know if that would be any easier. 50%, 84%, 97.5. So 1 minus. Probably not easier, but I guess I'm just trying to demonstrate there's a lot of ways of getting this, and a lot of ways of doing this. There's not like the right way. Find a way that makes sense for each question. This shouldn't be a magic trick, but this to me is really the hardest thing in this section, and it's going to be the thing that is most highly tested. So focus on that.